we consider really the flux of those, you have to multiply with the density of those particles as well. At least those which are in the cross section and capable to hit the target. Otherwise, it's not correct. This formula. So it's only for one particle target which has 100% probability for collision. Yeah, and this point here, also that's shown as a dashed line basically. The transition from glow discharge to the arc discharge may happen even like this or even like that. It depends very much on the electrode system, the impedance of the external circuit, and so on. So that's it. We will not actually go to that. I think when Elizabeth Linda will talk about circuit breakers, that's a subject for that technology, transition to arcs and arc interaction. So she will maybe talk about this. Okay, so non-elastic collision. So far we were talking about just two solid spheres which collide, transfer the impulse, and the particles may go in different directions depending on the angle that their velocity are forming actually. Yeah, but if the internal energy of colliding particles changes, we talk about non-elastic collisions. So they are associated with energy transfer, not only impulse transfer. Okay, what happens? We have electron, neutral particle. Electron just hit the particle. The energy may be not enough to fully ionize, but molecular or atom has electrons orbiting, right? So, and then another one coming. There is always interaction, right? Negative electron coming to some negative cloud formed by electrons associated with the heavy particle. So these Coulombic forces try to distort the electronic shell, leading basically to maybe some vibrations, what may happen in the molecular level, or rotation of this molecule. So excitation, that's what is called, happen. It may be rotation or vibration of the molecule without actual ionization. And then we consider two levels. It can be metastable, what is called level, with very long excitation time. It can be from milliseconds to tens of seconds lifetime. So it collides and then still vibrating or rotating. These all kind of related energy losses. Or what is called resonance level. It's the very fast. So it collides and then goes away, and the molecular just was very shortly distorted and then back to normal state. It's nanoseconds or maybe tens of 100 nanoseconds. This is very important for the probability of the breakdown, because if it's a metastable state, then next electron coming can ionize it and needs lower energy than the original one, because it's already excited. So the electrons are on the higher level and less or weaker connected to the nuclei. So that's the difference. Okay, and now comes ionization potential. So if electron has enough energy to ionize molecular or atom, ionize, that means the Coulombic interaction is such that external electron of the molecular or atom, which has the weakest coupling to the nuclei, can be released. Okay, that's what is ionization potential. Is the potential difference, which should be passed by electron in order to gain energy enough for ionization of the atom or molecule. Depending on the type, it can be this range. So surprisingly, the highest ionization potential is up to 25 electron volt, and yeah, one can expect basically that, okay, perhaps perhaps this is the strongest gas, because you have to have enough energy, but this is not really, it's one of the weakest gases, because ionization is not only about this, how much energy, but also about the cross section, how you transfer this energy to the to this electronic shell. So it's very much dependent on the structure, electronic structure of specific atom or molecule and so on. So this is not very much representative, but good to know. The lowest is for vapor of cesium, which is just almost 4 electron volts, so big difference. There were some technologies developed for space applications before, which were called thermoelectric generators, where actually the current passes through the vapor of cesium gap filled, the gap filled with this one. Just using this fact that it has lowest ionization potential, and then you can heat up the electrode, which produces the thermionic emission with quite low energy of electrons, still enough to ionize this, and then you may have some multiplication effect out of this. I don't know if this is used so far or not, but there was some development in this area. Yes, this is another thing. Ionization cross-section is always lower than cross-section of elastic collision. Ionization cross-section, yes. Excitation cross-section may be quite high compared to ionization cross-section, because for excitation, it's not necessarily that electron really hits the molecule. It can pass by, and Coulombic interaction is proportional to 1 over r squared, right? So it can pass by, not necessarily even colliding with the atom or molecular, but just the close vicinity, and that makes the cross-section larger because of the Coulombic interaction. But for ionization, you really need, well, not really need, but there is a need to in the directive mode. Yeah, and I mentioned already stepwise ionization. So the first electron collides with molecular or passing by, exciting this. Next one comes and needs a lot less energy to ionize it. So it's from excited states, yes. Important process in some applications. Generation of charge carriers, how this happen? These are notations which I used a lot in plasma chemistry. So you have atom, or molecular impact of electron. What happens? You have then positive ion and electron, then another electron. You need to have a balance of the densities here. Or, so this is electron impact ionization. Another way is electron and photon with frequency high enough to exceed the level of ionization threshold, and that's the result in the positive ion and electron. So this is photoionization, right? A plus B creating A plus and electron. So what is this? Two neutrals collide. This is thermal ionization, right? And the thermal energy is high enough, so that may happen. And you see, typically, if it's A and B, they are different type. For this reaction, the ionization potential of A is lower than the ionization potential of B. So that's why electron is provided by this particle, and this one just carries the excess energy after collision. Why I'm talking about excess energy, because this is quantum process. So you have orbitals, and then these orbitals, they have certain quantum number. So the energy which corresponds to this should be the portion should exact match to this. Otherwise, you need the third particle or radiative photon or something which takes out the excess energy. So in this case, the excess energy is taken by this one. Ionization from excited state, stepwise. So you have already an excited atom or molecule from this reaction, for example, when not ion is created by just excited state, so that there will be no another electron, just excitation. But then this excited one meets the electron, and then this happens. Or it may be the same story for photoionization, the same story for thermal ionization. There could be what is called associative ionization. Sometimes two particles can meet, create molecular ion, and release electron. Example here. Helium atom collides with electron and gets some excitation energy, and then this excited atom meets the neutral one, and they can move. They can create actually molecular ion and release the electron. So this may happen also. There is something that is called Penning ionization. That happens when the excitation energy of one neutral particle is higher than ionization level of another one. Then you have excited state of A colliding with B, and the ionization threshold of B is smaller than this one. So then this can be just released electron and then come to the neutral state, but the excess energy goes to excitation of that. Quite typical reaction for mixtures of Newton, no, how they call it. Argon, ion, helium, they are inert gases. Okay, quite typical reaction for that. And here is the reaction between the excited neon and argon atom. That's what is happening. Neon gives its excitation to argon and ionizing it actually. This is the fact that because of the fact that ionization energy of argon is lower than excitation energy of neon. So quite typical reaction for these lamps, because they are filled with these mixtures of gases. So it's in practice, I already mentioned this branch of technology which is called plasma chemistry. It's people just doing this chemistry with electrical discharges. So it's huge tables of different reactions, what they produce, how the conditions should be for this and that. And then this is used for many different branches, like treatment of surfaces, how they activate bacteria, even like this. So for this you need to know how to produce the required substances. Yeah, I will not go to details here. So this is about generation. What happens with the loss? You may have ionic species carrying the charge, and they can be lost in the discharges, right? What are the mechanisms? First of all, recombination. So this is just exactly the same reactions like here, but from the right to the left. You see these arrows, they are both sides. So you may have even like this, three-body collision when the conditions are suitable for that. So this ion can recombine with electron if the energy is maybe lower enough, and then create a neutral one. Usually it's excited, it's not matching exactly the quantum level. Yeah, this may happen with this one, so it's quite often Negative ions. Some gases form negative ions. That's typically, yeah, these ones. Oxygen, water vapor, CO2, SF6. They have something which is called electron affinity, which is not zero. So their atomic structure or electronic structure is such that there is a vacancy in the terms of potential energy where the external electron can be attached. Yeah, for example, in such reaction, you have two molecules of oxygen meeting electron. What may happen, one of them will absorb this, and then the second one just takes the, again, excess energy, because yeah, this is quantum reaction in a sense. Yeah, or this can be this way in two-body collision, not in three-body collision. One can actually have dissociative type of reaction when this one dissociates into atoms and one of them takes the electron. So this is highly oxidizing substance. Detachment. So attachment, when negative ion is created, also can be detachment. So when this atom is, or negative ion just loses the electron, is the opposite. So it can happen like that, for example. Typical in air, there is a negative ion of oxygen meets the atom of nitrogen, and then it creates nitrogen oxide. So and release the electron. It's all about the consideration of energy and how particles meet, how they transfer the energy and how they transfer the momentum. It can be, yes, also ion-ion recombination. That's also a mechanism of losses of ionic charges. Two ions meet, negative, positive, so they are transferring electron from one to another. Usually the result is one of the excited states, or they could be three-body collision like that. In this case, excess energy is taken by the servo. So this is typical reaction in air, because in air we have many components. We have oxygen, which is electronegative, especially water vapor. Then we have nitrogen, we have CO2, we have many components which make this reaction highly probable. Yeah. Now comes to the point. What is electrical breakdown? So we know now what happened here. So we have some particles which are bound by external factors. Then by applying the electric field, we have this region where particles can be multiplied because of the impact ionization, photoionization, thermalization, not probable here, it's mostly here. So, and then the current at some point becomes so high. The current simply means that the number of charges in the certain unit of volume per second becomes so high that it starts to support itself. So then this happens. This plasma region doesn't need any more so high energy from external power supply that it can support itself. Then the current goes like that, the voltage drops, still some voltage is needed to support the processes, but large portion of that just goes automatically, it's self-supporting. So, breakdown process is associated with an increase of concentration of charged particles here in dark discharge, tungsten discharge, electrons and ion in the gas through ionization process. As a result of electric breakdown, gas changes its properties from insulated to conductor. So here, you remember we calculated the conductivity like 10 to minus 13 Siemens per centimeter, just because of the low number of charges, which was like 10 to 3 per cubic centimeter, right? Basically, so it is protected. But here, we have typically the breakdown something like 10 to 13 at least electrons per cubic centimeter. That's 10 orders of magnitude increase, which gives us roughly 10 to minus 3 Siemens per centimeter. So basically, at this point, the gas is converted from being an insulator to more or less like semiconductor. And then further processes can increase it to be perfect conductor in the arc discharge. But that's another story. Again, we are talking about this. So that's what I want to stress. Discharges, electric gas discharges, is the term describing all these things. Electric breakdown is just one point here. Nothing else. Don't talk about this as a breakdown, because that makes no sense. So electric discharges, that's what this diagram is about. Yeah, and usually it's quite a boom depending on the external circuit. There was already a lab yesterday, right? Which I was confused about why it was scheduled before the lecture, because somehow, you know, there was no theory behind it. Okay, but I think Daniel succeeded to give you some input, right? And you had first course somehow, high voltage course, maybe that was not so unexpected, I would say. Yeah. If you're lucky, we are lucky to catch some real testing in Ludwika. You will maybe hear how this breakdown happened in the real system, not like in the lab where it's just very soft, I would say, in the sound and visual appearance. If it's really big high voltage component under testing, destructive type, so it's completely different story. People actually usually, it's like a local lightning, you know, impact, which is really loud and bright, and yeah. In the industry lab, people usually sit in the separate room, just protected from what is happening in the test field. Okay, but that's another story. Let's look on the characteristics. So the key process which leads to the breakdown is ionization. And if we talk about impact ionization, one of the main processes, so what is the characteristic of that? There is something that is called ionization coefficient, which is the number of ionizing collisions produced by electron per unit length of its travel in the field. So basically what it says, there is an electron, there is a neutral somewhere. The electron is exposed to the external field, it gains energy in this field, and then there is a certain path which it goes, and at some point that collision happens and it leads to ionization, right? So, and number of such events per unit length of the travel in the field. So the necessary condition that on this length the electron gains the ionization energy enough for ionization. So that's usually how this coefficient is expressed. It's called reduced form. So it's divided by pressure. And the field, respectively, field strength, also reduced field divided by pressure. That gives, it's like for mobility, but for mobility, usually it's used multiplication by pressure to have kind of generalized data. For ionization coefficient, it's divided by pressure. So here is an example. You have alpha over P, centimeter torr. Here you see torrs. That's what I mentioned. Torr is a millimeter of mercury column. And here is the reduced field, volt centimeter torr. So 5 different sets of data produced by different authors. That's why it's reduced, because they maybe made these tests for different conditions. But they all more or less on the same line, with some deviations, of course. Yeah, that's what it says. Ionization starts here, right? Because, yeah, below this level of the field, nothing happens. No ionization possible, the energy is lowered. And then when you increase the field, the intensity of this number of collisions per unit of the path becomes higher and higher and higher. At some point it saturates. So, but the important thing to remember, there is a threshold which corresponds to the energy, which is the minimum for ionization. Electron avalanches. How the multiplication happens. We have, let's consider this. Cathode and anode. We apply just DC. And what will happen? We have some electrons which may appear in the volume because of cosmic rays, for example. 1,000 per cubic centimeter, right? This is one of them. Or there could be some UV light radiating the cathode. If the frequency of these photons high enough to higher than work function of the material of the cathode, there will be some photocurrent or electrons released due to the photo effect. There could be injection from some imperfect surfaces. You have some roughness, and then you have the sharp protrusion, and then you apply the field, and then what may happen from this protrusion, there could be also charges injected. Okay, all this they put in motion because there is a field here between plus and minus. So the electrons, they move opposite to the field, right? Towards the positive electron, these ones. And the ions which are created, they move just opposite. Ions will be created due to ionization collision. So these guys, they start moving, they gain the energy, Q, E, lambda, which exceeds the ionization potential, and they create this one. Now we have two of them. They start basically from, one of them definitely starts from zero. Another one maybe have some already energy after the collision. So they accelerate again, passing the free path and meet another one, and eventually this happens, right? So you have a lot of ions slowly drifting backwards towards the cathode, and you have the cloud of electrons which move to the anode quite fast. There could be also some recombination happen between these two, which may lead to release of photons. These photons, that's why you see actually from the discharge, you see this normally in air, some UV blue light. These are the photons generated due to the recombination, and when they reach the cathode and have enough energy, so they can release secondary electrons, right? That's what may happen here. Or these ions reaching the cathode also have some energy. If this energy exceeds the work function of the material of the cathode, so there could be injection of secondary electrons by that mechanism. And that's what I mentioned already. When electrons reaching the anode, you measure the external current here. You just put an amperemeter sensitive enough. So you will get very strong peak here because of these electrons arriving to the anode. And then you will have quite a slow increase of the current because of the ions coming here. But then at some point it also will create some rather broad peak because of the, yeah, it starts with a low amount and then it comes to the higher number of ions reaching the cathode surface. Yeah, so how this is described, the expression for the current looks like that. You have initial current because of these processes, maybe photo effect or whatever, as I mentioned already. Then we have exponential growth of the number of electrons, well, not only electrons but actually charged particles. So this exponent alpha d. D is the distance between electrodes. And then in the denominator we have this expression here. So basically this one describes the yield of secondary electrons from the cathode. Gamma is the coefficient which says how many electrons are released due to the impact of positive ions. And usually for air and say copper, this type of combination, gamma at atmospheric pressure is about 10 to minus 4, 10 to minus 3, meaning that one electron is released statistically by due to the impact of roughly 1,000 or 10,000 ions, something like that. One of them has enough energy to release secondary. That's again statistical parameter. It's called secondary ionization coefficient. Yeah, there is a derivation for this expression. I will not go to details here, but maybe I will put it on the website so you can look yourself how this one can get this. So this is the current for this dark discharge, for this region where the multiplication happened. I0 is this level, and then this describes the rest of the terms, describes just this curve. Okay. Self-sustained discharge, when this happens, actually we can say virtually the current goes to infinity. So it's very sharp transition here. Then if the impedance, depending on the impedance of the external circuit, you may have some kind of significant drop here. But mathematically we can assume that, okay, the current goes to infinity. There's the breakdown. At what condition that happens? When denominator is 0, right? And that's what we do. So we take this one, equal to 0. This unit comes to the right. We have gamma, and then this term in bracket, equal to 1. And then just rearranging this, we can get this. So basically, yeah, transforming this even further, one can get the condition. So alpha d equal to 1, and that will give exponential alpha d equal to 1 minus gamma, 1 over gamma, and then you have taken the log of this, alpha d equal to log 1 over gamma, right? So this is the condition for the Townsend breakdown, what is called here. So this Townsend breakdown, Townsend mechanism is supported by the secondary processes on the cases, by this one. And this is different from another mechanism which we'll talk about later, which is called streamer breakdown. So Townsend breakdown, supported by secondary processes. This gamma is about yield of secondary electrons from the cathode surface. Okay, questions? Yes, this mechanism of breakdown, Townsend breakdown, is valid when the product of gas pressure and electron spacing V in a plane uniform gap is less than 1 bar centimeter. So basically, short distances, rather short distances at normal pressure. So if pressure is 1 bar, so Townsend mechanism usually valid in the gaps which are shorter than 1 centimeter. Or if you go to reduced pressure, you can consider larger distance. It's a product, P and D. That's what is called similarity criteria. Or not criteria, factor. What happens at higher values, that's we will consider later. That's what I mentioned already. It's a streamer type operator. Okay, below this limit, the space charge of the avalanche is rather low. So we have certain number of ions, certain number of electrons per unit volume, their concentrations. If we multiply this concentration with the charge, elementary charge they carry, right? We will have Coulomb per cubic centimeter, right? It's a space charge density. And that's what it says. So if we consider ionic space charge and electronic space charge, so that will be the total space charge, Coulomb per cubic centimeter. So it's not enough to distort the external field. So those of you who took electromagnetic force should recognize this equation. This is Poisson equation, right? You have Laplacian, potential, and then you have the space charge density on the right. So if this is 0, then it's Laplace equation, right? So this is Poisson equation in this case. So if the space charge is low, we have right hand side close to 0. So the electric field is decided by the geometry, basically. So there is no impact of this discharge on the electric field. But if this becomes high enough, then the transformation of electron avalanche type of discharge to another type, to streamer discharge happens. For now, we will focus mainly on Townsend type of breakdown. Streamer mechanism will come later. Paschen law, what is this? This is kind of similarity law which shows that breakdown voltages in the uniform field between parallel plates are the functions of this product, pressure and the distance between the electrons. So if we slowly increase the voltage across two parallel plane electrodes, electric breakdown of the gas will happen at certain critical voltage, which is the breakdown voltage, and the experimental data can be generalized in this form. So this is very widely used in practice, despite of the fact that this is only valid for uniform field conditions. Equally valid for even weak non-uniform fields, not for quantitative but qualitative analysis. The thing is that this is unique law for each gas or gas mixture. So how this look like? So this is the product of PD bar millimeter here. Okay, let it be millimeters. And this is the breakdown voltage. So usually the curve look like that. This is for air, 20 degrees C. So it's it has a minimum here. And if you talk about normal conditions, okay, we have pressure 1 bar, and let's take 1 centimeter, then we know that the breakdown voltage should be 30 kilowatt by 30 kilowatt, right? So 1 bar multiply with 10 millimeters, that will be 10. So we roughly here, not roughly, but here. So we could go here, and then we get, so 10, 20, 30, it's log scale. So 30 kilovolts, yeah, that's right. In this way, you can estimate any combination. For example, you have 10 millimeter, 10 centimeter gap, but the pressure will be, say, 100 millibars. Okay, so 0.1 bar multiply with 100, so you arrive to some PV, and then you take this value here, and then you just get the voltage there. So it's a combination of the distance and the pressure. Okay, that's how it can be used. Yes, and this curve is described actually by this expression. So I think at some point I will show you how to derive this, because it's quite often comes on the exams. Yeah, it's not rocket science, it's just a few lines of formulas, because you have to start with this condition. Yeah. And then express alpha with some given empirical expression, let's say. And then, yeah, just assuming that breakdown voltage is the breakdown field multiplied with the distance, you just rearrange the terms and arrive at this. So A and B, they are empirical coefficients describing the alpha, basically. So, but yeah, this is just the formula which shows that breakdown voltage is proportional to the product of PV. And then also in denominator you have also log of PV. That's what brings some kind of nonlinearity. Otherwise it will be just straight line. Yeah. The question is, yeah, let's look now here, and then we will discuss why we have a minimum. Yeah, as I said, this is unique for each gas or composition of gases. This is for air, this is for hydrogen, this is for neon. So if you have a mixture of gases, you can tailor actually the electric stress. The breakdown voltage. The uniqueness of this comes from the fact that alpha is unique for each gas. Conditions for ionizations, they are unique because they are defined by the cross-section, distribution of energy of electrons, and so on. So there is a minimum. What this means? Okay, 45. But I will finish with that, and then we take a break. So one can take the derivative and try to find the PD which corresponds to the minimum here, and then respective minimum breakdown voltage. So it's more or less like mathematical exercise based on the expression I showed before. Yeah. But physically, what happens here? Why there is a minimum? So basically, this is all about conditions for ionization. So at this pressure and the distance, so the free path is used kind of fully. So you have electron which just for the corresponding free path gains energy which exactly matching the energy needed for ionization. So the conditions for this, they are ideal, more or less, and then you have the minimum breakdown voltage, minimum strength of the gas. If you go to the right, more and more neutrals appear, and the electron meets neutral molecules before it gains actually high enough energy. And the higher you go in pressure, so more and more this happen, and then you need to apply actually higher field to recover conditions for the ionization. That corresponds to the higher breakdown voltage. On the left branch, you go down in pressure, and at some point, so what's happening, it's not enough neutrals to collide with, right? Not each electrode actually meets the molecule. Some of them just go through the gap without colliding with anything, just to the electrons, to the surfaces of the opposite electron. So for this, you need to again increase the voltage to provide conditions for the breakdown, even with those electrons which meet or capable of meeting the neutral part. At some point, you arrive to the conditions when there is nothing to collide with. And then it comes to the vacuum breakdown, which is a different story and is all about the injection of particles from the surfaces of the metallic bodies. So here is ideal conditions for energy transfer between the impacting particles and accepting the energy, so for ionization. So that's the explanation. Okay, let's take a break, and then I will continue with the